Welcome to the deep dive. Today we're getting into something really significant, what is essentially the master blueprint for the auto industry's next couple of decades.
It really is. We've got our hands on an intensive, almost consultancy-level research report.
The Automotive Lightweighting Technology Roadmap. And its goal seems to be to just fundamentally redefine how cars are designed and built all the way through 2040.
It confirms a huge shift. Lightweighting is no longer a niche discipline. It's become the defining strategic challenge of the electric era.
That's a big statement. For decades, it was just about fuel economy, right? Shave off a few grams here and there.
Exactly, a secondary objective. But today, it's the main leverage point. It's how you manage performance, range, and safety, especially in these new electric and intelligent vehicles.
So what's driving this new urgency? You mentioned the electric era, and the numbers here are pretty stark.
They are?
The sources state the conflict very plainly. Pure EVs are just inherently heavy. Because of that massive battery pack, they're over 20% heavier than a comparable gas-powered car.
And that 20% is the anchor they're all dragging. But the problem, it doesn't stop there.
Right. You have all the new tech.
Think about what you need for autonomous driving. Massive sensor suites, LiDAR, radar, computing clusters, just kilometers of wire.
Every single piece adds more weight.
It's all incremental mass. If they don't fight back with really aggressive lightweighting, they're sacrificing range and just pushing the structural limits of the vehicle. It's an engineering battle against compounding weight.
So that's our mission for this deep dive. We're going to guide you through this high-stakes challenge. First, analyze the status quo. Did the industry actually learn from past mistakes? Then we'll define the three core technical battlegrounds that will decide who wins. And finally, we'll walk through the official three-phase roadmap all the way to that 2040 vision.
It's a total system overhaul. Let's start with where we are right now.
Okay, let's unpack that. Before we look forward to 2040, we have to look back. How effective were the previous efforts? Did the industry hit its targets with RoadMap 2.0? Sounds like a mixed report card.
Absolutely mixed. You see these spectacular successes in new energy vehicles, which proves the potential is there.
Right.
But there was real drag from the conventional segments. When the industry applied lightweighting to a clean sheet EV platform, they crushed the targets.
So what was the biggest success story?
The report points to new energy passenger vehicles, especially in the smaller segments. They saw revolutionary gains.
And we should probably define how they measure this. It's the lightweighting coefficient.
Right. It's a key metric. It basically measures how efficiently a car maker has reduced the vehicle's mass relative to its size and function.
So a lower number is better. It means you've delivered the safety and the tech with less physical weight.
Precisely. And in the micro EV category, that coefficient dropped a phenomenal 42% compared to the 2019 baseline.
22%, that's way ahead of schedule.
Far ahead. And you see similar success in public transport, like buses and light commercial vehicles. They all met or exceeded their goals. It just proves that when you design an EV from the ground up, the gains are huge.
But where that EV transition wasn't happening, the conventional market, the story is a lot messier. What was holding back the traditional gas-powered cars?
That is the classic conflict, isn't it? Engineering versus the consumer. Conventional fuel cars only saw a 5.4% coefficient reduction. The target was 10%.
So they missed it by a mile. Why?
Because engineers were trying to cut weight, but what were consumers demanding? Bigger SUVs, higher safety ratings, more luxury features.
Panoramic roofs, massive screens, soundproofing.
Every single piece of added comfort or tech is mass. It directly counteracts any gains you make in lightweighting.
So if you shave, say, 50 kilograms off the frame with some new steel, but the customer wants 80 kilograms of leather and speakers and glass, you're actually going backward.
That's the exact dilemma. And you see a similar thing happening in heavy commercial trucks. Heavy-duty tractors barely moved, only a 4.6% improvement when the goal was 12%.
Wow.
It just shows that the older volume-driven segments, they don't have the incentive or the flexibility to make these radical changes quickly.
Okay, let's pivot to the competitive landscape. Looking at this as a strategic document, was there a clear winner identified between the domestic brands and foreign players?
This is one of the most interesting parts of the report. Domestic EV brands have a clear and growing advantage in those key mass market segments.
Like SUVs.
Compact, mid-size, and large SUVs, yes. Their lightweighting coefficients are averaging over 20% better than foreign brands in these categories.
20% is not a small gap. That's a generational leap.
It is. It suggests domestic innovation is leading the way in integrating the battery and the structure much more efficiently.
But you mentioned weak spots. Where are they lagging?
The weak spots are almost always tied to legacy thinking. Domestic performance lags a bit in smaller SUVs and some midsize cars.
Yeah.
And you can trace the root cause right back to vehicles that were just modified from old gas-powered platforms.
The oil to electric conversions.
Exactly. You just inherit too much heavy, inefficient structure when you try to force-fit a battery into a chassis that was designed for an engine and a transmission tunnel.
And that brings us right to the path forward. If the old way is the bottleneck, the industry has to pivot. This roadmap lays out 3 synergistic technical pillars.
These are the 3 battlegrounds. They're attacking the problem from design, materials, and manufacturing all at the same time.
This is where it gets really interesting for me. Let's start with Pillar A, architecture and integration. This feels like the most radical change, treating the car not as thousands of little pieces, but as a handful of massive integrated systems.
That is the core of it. We're moving beyond optimizing a single bolt to integrating entire systems, and the first key innovation here is component integration.
Which everyone now knows as gigacasting.
Gigacasting, yes.
Yeah.
The process that Tesla really popularized, where a whole complex assembly, like the entire rear floor, is cast in one giant piece.
Eliminating dozens of parts, joints, hours of work.
Exactly. And the report notes that domestic adoption is happening fast. Take the Chang'an Kiyuan EO7. It integrated an incredible 90 parts into a single rear floor casting
90 parts into one.
and achieved a verified 20% weight reduction just in that one assembly. It cuts weight, it cuts complexity, and it shortens your supply chain dramatically.
But I have to ask the obvious question here. If you cast a major structural part like that and it gets damaged in an accident, isn't the car just a write-off? It seems incredibly expensive to repair.
That's the critical tension, you're right. Repairability is a huge challenge for the insurance industry. It forces a complete shift in how accidents are assessed.
So what's the solution?
The engineering benefit, the weight reduction, and the stiffness is seen as worth that disruption. The solution lies partly in designing smarter modular bodies with crush zones that can be locally repaired, even if the main casting is one giant piece.
Okay, the second integration area is the battery itself. Cell to body, or CTB, and cell to chassis, CTC.
CTB means the battery is no longer just a separate box you bolt underneath.
It becomes part of the structure.
A fundamental load-bearing part of the structure. The B-body seal is a prime domestic example. They use CTB to hit a torsional stiffness of, get this, 40,500 newton meters per degree.
Wow, that's supercar territory.
It's structural rigidity you'd expect in a high-performance sports car, and the sources say domestic CTB is now right on par with the best international standards.
And CTC, the skateboard chassis, takes that even further.
CTC is an even deeper integration of the battery, the motor, the control systems, the 3 electrics into one flat rolling platform.
A skateboard.
The report does acknowledge that while the domestic industry is catching up very fast, international players like Rivian or Canoo still have an edge in the mass production of these true skateboard platforms.
And the final piece of the architecture puzzle is the most futuristic, AI integration. How does AI help make a car lighter?
The current R&D cycle for a new car is just too long, too expensive. The idea is to use AI large models and digital twins to completely revolutionize design optimization. An AI can simulate millions of structural permutations. It can find the optimal arrangement of materials and stress points that a human engineer might never even think of. It's about cutting the development cycle from years to months and getting maximum efficiency at the same time.
Okay, so we've designed these massive consolidated structures in Pillar A, but that only works if the actual materials are lighter and stronger. Which brings us to Pillar B, advanced materials.
Right. We are seeing a complete overhaul of the material diet of a modern car.
What's changing?
If you look at the trends over the last decade, usage of older stuff like soft steel and even high-strength steel is just dropping dramatically.
Oh.
Over 50% and 30% drops.
Steel's replacing it.
The entire push is toward materials that give you maximum strength for minimum mass. So ultra-high-strength steel, or UHSS, and hot-forming steel, PHS.
So steel isn't going away, it's just becoming exponentially tougher. Can you put that strength into context? What does 2,500 MPa steel really mean?
Okay, so PHS usage has gone up almost 7 times since 2013. And MPa measures tensile strength, how much force it takes to pull it apart. Standard car body steel is maybe, 300 to 500 MPa.
And the new stuff.
The current focus is pushing PHS to 2200, even 2500 MPa. To put that in perspective, that's approaching the strength-to-weight ratio of high-grade aerospace materials. It means you can use paper-thin sheets of this in the safety cage and get better crash protection with way less weight.
And this is tied to climate goals, too.
Critically, the report mandates that this leap in strength has to be paired with sustainability. They're targeting a 70% carbon emission reduction in steel production by 2030. It's not enough to be strong. It has to be green.
Let's talk about the true light alloys, aluminum and magnesium. The sources cite some explosive potential here.
Magnesium especially is the big material of opportunity. That large-scale casting we talked about in Pillar A is what's driving this. Magnesium is 35% lighter than aluminum by volume, but it's always been tricky to work with at scale. Now we're seeing development in these huge MGAG cast parts over 2.2 square meters, and compared to an equivalent aluminum part, these magnesium castings get a remarkable 32% weight reduction.
32% is a game changer. And that's not just about performance, is it? That saving translates directly to cost.
That's the critical connection. Every kilogram you save structurally is a kilogram your battery doesn't have to move.
So you need a smaller, cheaper battery for the same range.
Exactly. It creates this cascade effect on cost, on battery size, on charging time. It makes magnesium a huge economic driver, even if it's complex to process.
And what about new composites moving into structural rules?
They're moving beyond just interior trim. The roadmap is really focused on basalt fiber reinforced composites, or BFRP.
Basalt fiber.
It's made from volcanic rock, so it's very robust, very high strength, up to 4,000 MPa. But crucially, the manufacturing process is inorganic, it's green, and has low carbon emissions. It aligns perfectly with that 2040 vision.
Which leads us perfectly to Pillar C connection technology. So we've designed these giant components, and we're using ultra-strong steel, aluminum, magnesium, and carbon fiber all on one car. How in the world do you stick them all together reliably?
This is the critical bottleneck. It's the weak link that slows down all this multi-material innovation.
Because you can't just weld them.
Your traditional spot welding doesn't work well when you're trying to fuse steel to aluminum, so multi-material design forces you to use new techniques. Self-piercing rivets, laser welding, advanced adhesives, and something called friction stir spot welding, or FDS.
Let's focus on FDS. Why is that one so important?
FDS is vital because it uses friction to heat and fuse two different metals without actually melting them completely. It bypasses all the metallurgical problems you get with traditional welding.
And it's fast.
The domestic industry is very competitive here. The connection time for FDS is around 2 seconds. That's rapid.
So the speed is there. But the report flags a big lag in evaluation. Why is that the weak spot?
The report points to a major gap in standardized performance evaluation methods, and more importantly, in the digital and intelligent monitoring of the joint quality during mass production.
So you can make the weld in 2 seconds.
But if you don't have an intelligent system verifying the exact strength of that joint, in real time, your quality control suffers. That lack of monitoring is what's holding back the scaling of these multi-material designs.
Okay, so now that we've seen the challenges in the 3 technical battlegrounds, let's look at the blueprint itself. The ambitious 3-stage plan for the next 15 years.
Phase I takes us from 2026 to 2030. And this is all about consolidation. It's about the accelerated industrialization of these known technologies.
What are the immediate goals for this near-term phase?
The targets are tangible: a 15% reduction in the EV lightweighting coefficient and a tougher 5% reduction for the conventional ICE cars. Light commercial vehicles also need to drop by 10%.
And what are the signature technologies we should see in mass production by 2030?
You should look for mass production of 2,000 MPa ultra-high strength steel hot stamped double door rings. That's that super strong crash structure steel.
Okay.
We also expect that integrated magnesium alloy rear floor casting to enter mass production. And critically, the industry has to establish a robust ETTC architecture design and evaluation system. Phase US is about getting the system caught up to the tech.
All right, phase 2 takes us to 2035. What's the shift here?
This is where the focus really shifts to materials dominance.
And the goals get steeper.
Significantly. The EV coefficient needs to drop by 25% from the baseline, and the ICE coefficient is targeted for a 10% reduction. The focus here is moving from just optimizing steel to really integrating light materials everywhere.
What manufacturing innovations define this midterm phase?
We're looking for specialized processes like laser-assisted hot forming of 1,800 MPa steel to become standard. More systemically, the report demands the full development of skateboard chassis design systems for both passenger and commercial vehicles
So moving it out of niche applications.
into widespread adoption. We should also see mass production of things like semi-solid magnesium alloy wheels and basalt fiber hybrid components in places like dashboard frames.
And finally, phase 3, the long-term vision through 2040. This is the frontier. What's the ultimate goal?
International leadership. The targets are pushing theoretical limits. An EV coefficient down 30% and an ICE coefficient down 13%. This whole final phase is envisioned as being propelled entirely by AI and low-carbon, super-efficient manufacturing.
What are the milestones that represent that total integration?
We're looking at the mass production of 2,500 MPa hot-forming steel, the absolute limit of what we can do with metallic materials right now. But more importantly, the soft targets are all AI. The widespread R&D and implementation of AI-based automotive lightweight innovation design software. This computational power is what enables the final, most futuristic milestones.
Which are?
The production of autonomous driving-based CTC skateboard modular architectures, including 3D printed bio-based ultra-material occupant compartments.
Wow, that's a massive leap. From stamping sheet metal to 3D printing passenger cabins out of bio-based materials.
That is the vision of total integration. If we sum up the key takeaway from this whole roadmap, it's that the future of lightweighting is a holistic, systemic challenge. You can't win by just optimizing one part.
No.
Success requires parallel breakthroughs in design, in materials, and in manufacturing, all synthesized and accelerated by AI.
Recapping some of the things that really stick out to me.
Yeah.
The leap to 2,500 MPa steel, the incredible 32% weight saving from those huge magnesium castings, and just the strategic push toward these massive structural assemblies, taking a car from thousands of parts to just a handful of modules.
And that systemic integration brings us back to that 2040 vision. The goal isn't just to find lighter things to build cars out of. It's about leveraging AI to design structures that transcend what traditional human engineering can even achieve, turning the vehicle into a total integration piece. Which leads me to a final thought for you. What stands out as the most revolutionary technology on this roadmap? The ability to 3D print a bio-based occupant compartment, fundamentally changing what a car is made of, or the AI design software that makes that kind of radical design possible in the first place?